This is the solutions to the 1988 multiple choice APC test. Number 1. This one should have been a fairly easy question. We're just looking for a distance versus time and a velocity versus time graph for something that's uniformly accelerated. Again, the distance versus time graph should be curved. The velocity versus time graph should be straight because we're showing uniform acceleration, so the answer was E. Number 2 and 3, we're using the picture from there where I have the 4 kilogram block moving at some velocity, so I looked at conservation of momentum. So the momentum of the first block should be equal to the momentum of the second block. They're the same mass, so they'll have the same velocity. Once that one moves into the other one, it transfers its momentum in there, so you can see that I took 4 times 6, so 424 is equal to 8 times v, solve for v. So the answer to number 3 was C, and then the answer to number 2 was 0, so the first one transferred all of it. Number 4, we're looking at the mass of a block that moves on a straight path. Oops, hold on. Mass of a block that moves on a straight path, and it's given a function for that velocity, and we want to find the magnitude of the net force. To find the force, I need a mass times an acceleration, so I took my velocity function and did the derivative of that to get my acceleration function, and then took the acceleration times the mass, and that's how I got the answer for E. Number 5, we have an object that is sliding down a frictionless incline. They gave us enough kinematic information to find the acceleration, so you can see that I did a d equals 1/2 at squared plus, the initial velocity was 0. Solve for my acceleration. Acceleration was 2. Plug that in then to figure out the distance that it would be after 2 seconds, and then do the difference between those two distances to find 3 meters. Moving on to the next page. Number 6, we have 2 people in a rowboat, and the 2 people in the rowboat are going along. Hold on. Where the rowboat can have a maximum speed of 5 kilometers per hour, and the river is moving at 5 kilometers per hour. So ultimately, my rowboater needs to actually move at an angle that would be going kind of up if it's going to be pushed back. I actually figured out what that velocity would be. It would be 5 square root of 2 for the velocity, but because they said that the 2 people are at a maximum of 5 kilometers per hour, the answer comes out being E. There's a point directly across, cannot be reached under these conditions. Number 7, we're looking at these 2 different vectors, so the first vector to the second vector, and we can see that we're changing our angle, and we're actually showing that it's going to be kind of a deceleration. You can see what I did here is I did a vector addition to see how big my angle would be, and I know that the resultant of my 2 velocities would be in the north of east, but the acceleration would have to slow it down, so my acceleration would have to be north of west. I'd have to show it as a deceleration in order for this to be achieved. So that's why the answer was E. Number 8, we had a projectile that was fired from a gun, and let me see. So this one was, this was a little tricky. I looked at it in terms of, here was my kinetic energy of my projectile, and with m1 being the mass of the projectile, v1 being the velocity of the projectile. And then I looked at it under a conservation of energy. So my conservation of energy was m1 v1 is equal to m2 minus m1 times v2. So there's my momentum of my bullet versus the momentum of the gun. And from there, I had to redo my work a little bit. Let's see. I set up this equation, and then I looked at it in terms of the kinetic energy of the gun. Kinetic energy 2, which would be the gun, would be equal to 1/2 the m2 minus m1. And now our new velocity squared. Then I did some algebra to solve for what v2 was equal to, and then solve what v1 was equal to, and then do my substitution back in. So you can see that v1 was equal to this 2k over m, or the square root of 2k over m, and then reduce down to the point where I get k2 was equal to m1k over m2m1, it looks like, minus m1. So answer was D. Number 9, we did not do a lot of talk about centers of mass, but what I kind of did in this one is, this is kind of one of those reasoning ones. If it was completely square, it would be passing through here and through here, so we would get it at the center. But because we're missing the little chunk here, if I was to balance in this direction, I'd have to be somewhat lower here, because I have more mass on this side than I do on this side. So I'm going to be something less than 1 on the y-coordinate, and then I have more mass over here on this side than I do on this side. So I'd have to be more than 1 on the x-coordinate. So I started to do a process of elimination. I knew that these two were incorrect because I couldn't be at x equals 1. I had to be shifted something greater than 1. And this one shows something less than 1, so I eliminated those 3 choices, got down to these 2 choices, and said that this one fits the best because I'm shifted over here and shifted down there. Number 10, we have a projectile fired from the surface of the Earth. Okay, what did I do with this one? So my projectile, it just was a standard projectile. The angle was 30, so the sine of 30 is actually 1/2, so half of 200 is 100. So that gave me a quick, easy way to do that one. And I ended up with an answer of 500. Number 11, we have our particle moving along the x-axis, constant acceleration. So my acceleration function was given to me. I needed to know where it was located, so I needed to get all the way back to a position function. So I first did an integral to get to my velocity function, so I got my integral and eliminated this t because we're starting at rest, and so because we start at rest, our initial velocity was 0, so that part would disappear. Then I did the integral of that to get to my displacement function, and then once I had my displacement function, I just plugged in a 2 and got the answer of 16. Number 12, when I looked at number 12, I was looking at this in terms of my figure skater. They're spinning around, and angular momentum is always going to be constant, okay, because we conserve that quantity. So in other words, I automatically knew my answer would either be A or E just because of that statement. Then I looked at it in terms of what happens with my kinetic energy, and if you think about it, I'm rotating slower when my arms are out, and I rotate faster when my arms come in, so I am seeing an increase in my kinetic energy, so the answer was E. Number 13, we have the ball is dropped from a height of 10 meters. Let's see, so again, I just set this up as a kinematic relationship and got to my answer, and it was not too bad. Hold on. I got to come back on 13. It looks like I skipped number 13. Okay, number 14. Number 14, the object is moving in a straight line of velocity. So again, I'm given a velocity function. The acceleration then would be the derivative of that function. So I did the derivative at 2 seconds, and that gave me my acceleration for A. And 15 was the displacement, so I did an integral of that and evaluated my integral between 0 and 6, and then that's how I got that answer. Number 16 is the pendulum consists of the ball. So again, I looked at it in terms of some energy statements. So I did a gravitational potential energy was equal to my kinetic energy. I then set it up knowing that a 60-degree angle, cosine of a 60-degree angle is actually half, so it's half of L. Did the algebra work to get the relationship V equals the square root of GL. So the answer was A. Number 17, we lift a rock up using some force, so we're looking at the work done by the net force was F minus W. So in other words, I'm lifting with F and the weight of the rock was W, and so subtracting those gives you your net force. And it was your net force to figure out the number of work. So that was number 17. And I think I'm going to pause here and make a second video then for the rest of the problems.